to have Jeanne. We're excited to have Jeanne here to present with us, because I know a number of us have worked with her over the years at Sandia, and she's done a lot of work broadly in the area of emerging devices and neuromorphic computing. And in particular, this is the COINFLIPS Seminar series, and Jeanne is a COINFLIPS co-PI. So this is the kind of an opportunity to have one of our co-PIs give a talk in this seminar series. So with that, I'll go ahead and hand over to Jeanne's presentation. Thank you.
Hi, thanks so much for the kind introduction. I'm really happy to be here and see all the great people on Zoom. So yeah, I'll keep going. And if anyone has any questions, feel free to just speak up, or if you want to put something in the chat, maybe Brad, you could then tell me if someone's in the chat so I don't miss it. Okay, so yes, I'm here to talk about our continuing work on using randomness and stochasticity in magnetic tunnel junctions for unconventional computing. So I put the acknowledgements up front. This is the results I've presented from multiple papers that involve multiple authors, so it's not an exhaustive list here, but I wanted to make sure to acknowledge the students and postdocs who are leading this work. So Sam Liu, Jae-Sik Kwon, who's a postdoc in my group, they are the main ones who worked on the simulation work. And Thomas Leonard and Harrison Jin have been leading our experimental efforts, while Paul Bessler is an undergraduate who has been working closely with the graduate students on applications. And then, yes, we've been very fortunate to be part of this COINFLIPS team. So these are a few of the members of the COINFLIPS team: Suma Cardwell at Sandia, Katie Schumann at Tennessee, Brad here, and Darby. And then for the second half of the talk on applications to Bayesian neural networks, we've been working closely with Chris Bennett and Patrick Shao, who led that work together with my student Sam. Yeah, funding is coming from Sandia and also NSF. So with that, I want to start with motivating why we are interested in materials and device-aware computing that leverages stochasticity and randomness. And then I will describe our results on two different topics. The first is understanding these different knobs we can use to control magnetic tunnel junctions as random number generators. So STT, SOT, and VCMA, I'll define all those. And then for the last part of our talk, our work on how we can design combinations of magnetic tunnel junctions and domain wall-based devices, and then apply them to Bayesian neural networks. So probabilistic computing is a large section of heavy data computing that relies on pseudo-random number generators to analyze really large-scale data problems. So here are just a few examples: the analysis of heavy ion collision data or other particle physics data. You can see it visualized over here. Or here's another visualization of human genome sequencing and all the types of really data-intensive biological applications that can rely on stochastic and random events. Another big area is in climate data. So this is just data points of different climate data observations that get put together in predictions about the weather. So for all of these applications, the random number generators are heavily utilized. There are a number of required random number generator properties for these applications. So this came out of this paper that we recently did with the COINFLIPS team. And we want to know the quality of our random number generator. So how good of a random number generator is it? Is it a true random number generator? We want to know the quantity. So can we create high rates, high speed, and also high volume of random numbers to then use in these algorithms and applications. And we also want to be able to set and control the type of distribution. So do we have a uniform distribution or a Gaussian distribution, or can we tune the distribution? And so within all this, we also want high speed, low energy, and robustness to temperature, since a lot of these RNGs are driven by thermal effects. So this is a long list of requirements for this device type. So like I said, there are a lot of applications already using RNGs. And so I tried to look through some literature on the status of current RNG-based computations based on CMOS. And here's one paper that came out in 2022, which is a nice summary. So here it looks at their energy consumption for these different types of RNG implementations. And so you can see the energy consumption is in the microjoules regime over here. Also, they have lists of the time it takes to generate an integer. So again, for these different types, you can see the average time can be quite long. So hundreds of microseconds up to tens of thousands of microseconds. We also can understand that that's just the energy cost to produce as close as you can true random number generator. But if we want to then go forward and tune those, the distribution of random numbers, then the energy and time cost balloons even more. So they use a method called rejection sampling to then pick certain results from the distribution of random numbers. And here again, this is from one thing I found about this rejection sampling on the amount of time it takes, for example, for different CPU and GPU methods. These are different methods that are used, and you can see it's on the order of milliseconds. So I think this is all a clear argument that we really would highly benefit from hardware-based true random number generators that can also satisfy all of that long laundry list of RNG properties, especially including hardware-based tunability, so we don't have to do this post-tunability that is very energy and time hungry. Okay, so with that, we can look to magnetic materials, and these magnetic materials provide many of the desired characteristics for computing devices in general. So we can make them into resistive memories that have fairly low energy to switch them and speed, very high speed to switch them, and traditionally applied to STT-MRAMs and memory technologies. They're non-volatile, so they'll keep their state. They're back end of the line compatible, so we can put them with CMOS when we create this RNG circuits. They have hardness to radiation, which is beneficial for extreme edge computing. And they have thermally driven magnetization dynamics that can be controlled with currents and voltages. So the basic building block for these RNGs is the magnetic tunnel junction shown here. So this is just a brief introduction to any of those of you not familiar with MTJs. So we can have two resistance states that depend on the relative magnetization of the magnetic electrodes. So when they are parallel, then a large current will tunnel across this MgO tunnel barrier. And when they're anti-parallel, a small current tunnel. And I realized I should put on my pointer. It's fine. You can see my cursor, I think. Okay, so we can electrically address these devices. So they can be electrically read. We read out the relative resistance by RP and RAP, and then we characterize it by this tunnel magnetoresistance, TMR, which is the resistance difference. And we can also electrically switch the magnetization. So this can be done using spin transfer torque, and that's when we pass a current through this tunnel junction and use the spin polarized current that's going through these magnets to then flip one of the magnets. And we can also use spin orbit torque, and that's when we instead pass current through the bottom electrode down here, and this can generate a spin current that can switch the magnet next near it. And we can also use other effects that we'll come back to. So magnetic probabilistic bits, or p-bits, are heavily studied today. So there's a lot of great work coming out, for example, from Karen Kansari's group and Supriyo Datta's group. I know Supriyo gave a previous talk in this seminar series. So largely today, the magnetic p-bits focus on what we can call unstable magnets, or a stochastic read, where, so here's the energy diagram of what it usually looks like. This is representing that we can have magnetization in one direction or the other, that's the red or the blue. And then if we have a very low energy barrier between the red and the blue, or between the two magnetization vectors of that magnet sitting in the little disk, then it can randomly thermally sample being magnetized up, down, or left, right over time. And then, so if you look at this random sampling over time, you can then bias with current, whether it's more down or more up at any given time. And And this is also shown over here in this paper from 2021, just showing this random sampling over time. And then sometimes it magnetizes one way, sometimes it's the other. So this is a nice way to produce random numbers because all you need to do is then just sample it over time. But there are many more knobs that we can use to control MTJ randomness. And when we think about satisfying that list of what's required for a random number generator, it's important to explore them. And so that's our purpose in this paper, was really to think about systematically understanding what other knobs we have to control the MTJ. So here's our MTJ again, like I showed earlier, and there's a lot we can do with it. So like I said, we can control the randomness of this 2-energy well state using spin transfer torque. So this will be current applied through the tunnel junction. We're going to call this going forward the stochastic right, or just the right method. So instead of having a low barrier magnet here, instead this magnet has a high enough barrier that the delta E is big enough that at room temperature it sits in one direction. And then for the right type, we apply a current through, and depending on the amplitude of the current, so it's sitting on one side, there's some probability of kicking it over to the other side. And so if it's a small current, then it won't kick over very often. If it's a big current, then it'll kick over. And so that's what the stochastic right type is. So we could also use spin orbit torque. So here instead, again, we're going to have a good energy barrier that's keeping our magnetization stable. And then if we apply a current along this direction through a heavy metal, we can generate a spin current. And that can take this magnetization actually from being perpendicular to in the plane. So it'll move from perpendicular. And then when we take away that current, it could then pop up or down. And we can do a similar thing with voltage controlled magnetic anisotropy, or VCMA. So in that case, we apply a voltage across the tunnel barrier. And depending on that voltage applied, again, it's going to decrease this energy barrier between the parallel and antiparallel states. And then when we take away that voltage, we can pop up or down. And so these are ways that we can create random numbers. And depending on the random magnetization after we apply the currents. And we also can be using these different knobs together. And that's why I'll show us some simulation work of how we can do that. So if there's any questions at this point, feel free to ask, because that's like the basics of it going forward.
I have a quick one, if you don't mind.
Yeah, no problem.
So the random, the random number generator aspect of this comes from the way the barrier reforms after current is turned off, whether it goes away or comes back. And you keep,
yes,
okay.
Yeah, and what side it's on when it comes back.
Whether it's like whether the magnetization flips up or down, you mean?
Yes.
Okay.
Yeah. Great.
Thank you.
No problem. Any other questions on the basics? Oh, okay. Okay. So to analyze what these devices can act like, we put together a macrospin model that's based on this Landau-Lifshitz-Gilbert equation, or LLG equation, that is a well-known equation that governs how the magnetization processes in space and time. And we wanted to go to this type of model since we often work with micromagnetic models, but those are very time intensive. So to generate large numbers of bit streams, really want to use some model like this. And so we can put in all the different driving mechanisms I just described, including this VCMA effect, which is modeled here, and including temperature, which is important for these R&Ds. So this is the table of all the physical parameters used in the model. And to be consistent across the different methods we can use to switch these devices, we just kept it all the same for standard MRAM-like structures. So cobalt iron boron, free layer, magnesium oxide tunnel barrier. And what we'll see later is that going forward, you really would want to tune the materials parameters more for each of these methods that we'd use to operate the devices. So they're all listed here, pretty standard materials parameters that are well known in the field. So using this model, we can see what happens more clearly in time as we apply either spin orbit torque current or this VCMA voltage. So on the left here is when the VCMA voltage is applied. So you can see the voltage is applied, and the magnetization starts out pointing in one direction down because that's perpendicular anisotropy. And then it has this precessional motion. It swings around and around the center point until it damps down and points in the plane. And so this is standard Larmor precession that you may be familiar with from nuclear magnetic resonance type effects. So we can see how we apply the voltage, we get to this middle state, and then when you take away the voltage, it's either going to go back down or it's going to go up to the other side. So for spin orbit torque, it's a little bit different. So spin orbit torque, we apply a current in the plane, like I showed earlier. For spin orbit torque, we also are assuming a small external field is applied. This is needed to break the symmetry and allow this SOT current to operate. And so here it has a field-like behavior where instead of precessing around, it has a more like it's following the field, an effective field over to in the plane. So again, but then it goes in the plane with the application of the current. Usually people use SOT and they apply more current than this and they flip it to the other side. But this is applying enough current to send it in plane, and then it's going to then choose whether to go up or down. So with that, we can look at these random bit streams. So here we took 20 samples over 200 nanoseconds for the 3 different ways we can operate the device. So spin orbit torque, this VCMA, or the stochastic right, where we're using the STT current through the tunnel junction. And so here I'm just showing the randomness of it by repeating it twice. So here is on the left for the spin orbit torque, this is the current of the spin orbit torque pulsed continuously. And then the blue and the green are 2 different runs. So this is magnetization over time. So you can see every time it's pulsed, the magnetization goes in plane, and then it goes either up or down. For VCMA, it's somewhat similar. Here, since the precession is a slower process, we didn't, to make it not too slow, we didn't want it to wait forever before we pulse it, before we move the voltage. So you can see here that it's going in plane, but it's not having much time to settle in plane before we let go of the pulse and let it go up or down. But we still can generate the random bit streams. And then for the right type, this one has a little bit of different mechanism because you always want to be switching it from one side of magnetization to keep it random. So we have a pulse, and then we have a read, pulse read. So it's like a reset read type operation. But we still get the magnetization either going from here, going from -1 to 1 every time we pulse it. So those are what the bit streams look like. We can then generate S-curves to look at how we can control the weight of these coins being generated. And so basically, as I said before, we not only want to generate the bit streams, we want to control the probability of being up tail to tail or +1 or -1. And so we can do this by using these various knobs we have. So this is for the SOT-driven RNGs, and then we can bias the coin using either spin transfer torque, so also applying a spin transfer torque current through the tunnel junction, and that's what's shown in blue, or using a field as well. We can bias it with a magnetic field applied, shown in orange. So this is just looking at the values of STT that you need to then bias, so it being always one direction, another direction, and in between. For VCMA, we again can bias with either current or field. And so you can see this behavior as well. And then for the stochastic right type, same thing here. When we say current, it's the amplitude of the current that we're applying through. So we're just using STT, but we're changing the amplitude of the current, and then we can change its weight. And so they all behave quite well. We can see that for the parameter simulated, the SOT and the VCMA had a more centered S-curve, which can be beneficial that you can achieve a 50-50 coin at 0. But this is, of course, in an ideal case, and it might be that you need to go to adjust for anything that are off from the ideal in an actual device. So, but for the right case, we saw that it was not as centered. And so we then did these tests for randomness quality, and all 3 methods passed the test well. So this test is of generating 8-bit numbers so we did over 10,000 samples, and we want to see if the distribution is uniform. And so what we can do is look at the density of what numbers are between 0 and 255, and we want to see that it's a somewhat straight line. And so to look at our biasing that we did this both for a 50-50 coin for each method, that's in blue, and then for a purposely biased coin, so 0.5 versus 0.6 weight. So the 0.5s are shown in blue, and you can see they all look nicely uniform, and then we can quantify how uniform they are by this chi-squared numbers, which look fine. And then for the slightly biased coin, we can see that we can visually see how the biasing starts to look, that we don't get this uniform distribution anymore as we would want. So this is just giving us the definition of this chi-squared value calculated from the data generated. And so one other test we did is this runs test. So again, over 10,000 samples for each type. And this looks at the probability of observing a given run length of ones. So making sure we're not getting a bunch of ones in a row when we shouldn't be. And so we want to match it, compare it to the ideal case, which would be the dashed lines, which is given by this equation here. And we see again that the 50-50 coins for each type all match this dashed line quite well. And then when we bias, we can see it nicely biasing away from that, as we would expect for all three types. So then we looked at the temperature analysis. This is looking at the three types again, and then for three different weights. So let's focus first on the 50-50 in the center here. So, and then it's 500 samples per point. So we're also getting some distribution on each point shown by the shading. And so at the 50-50 bias, we see very little temperature dependence. So as we increase from 300 to 500 K, and this is nice. So it's basically by having this fixed magnetization and then using this method of bringing it in plane and then popping it up, or using the amplitude of the current to determine whether it goes over the tunnel barrier. The higher temperature doesn't change the magnetization compared to the in-plane state. Everything kind of moves together so that the 50-50 stays pretty nicely at higher temperatures. We see that if we bias either at 0.7 or 0.3, so a higher bias or a lower bias, that we do see some increase towards 0.5 as we increase the temperature. So you can see this green and the blue curves are kind of going up to 0.5, and up here at the 0.7, we're kind of going down a little bit towards 0.5. And so we see that, if there's larger thermal fluctuations when we bias the coin, then we do need a larger bias to compensate for that. So this is all done in the same bias. So you could adjust for that by changing your bias at different temperatures. One thing to note is that the SOT and the VCMA type were highly robust in temperature. The right type, where we're using the amplitude of the ST current, it really depends on what regime we are using in terms of the current pulse that we're using to operate. So here we used in like the nanosecond regime current pulses, and we saw very little dependence on temperature. So we were in the ballistic regime, and that's where you would want to operate the devices to have no temperature dependence. If you go to thermally assisted regimes, it's like microsecond pulses, then instead we see the VCMA and SHG still have very stable weight versus temperature, but the stochastic right increases versus temperature. And then looking at energy analysis, we can calculate the energy as shown here. So over a certain pulse, we can consider both the energy from the VCMA, the spin transit torque, and the spin orbit torque. And so here's the energy in picojoules per sample versus the weight as we weight our coins. So a few conclusions from this is we see there's different, remember we were keeping all of these simulations with the exact same materials parameters. So with that in mind, the SOT came at the most energy efficient with around like 0.1 picojoules per sample. And it has a good stability over weight. And the VCMA came out as the most energy intensive, and that's really because we needed to put quite a high voltage, and we needed to operate for quite a long time to get that magnetization to process and then damp down to the center state. So this showed us that we would want higher damping materials to use the VCMA type. And then the stochastic right type was somewhere in the middle, around 1 picojoule per sample. We also see that the stochastic right time, again, had more of an increase has more of an increase in energy as we change the weight, and that's because it's mapped directly onto this amplitude of the current needed to set the weight. The VCMA and SOT types required smaller changes in the current to set the weight, versus the right type required larger, so there was more of an effect on the energy as we change the weight. So these can give us some numbers that we can then start to compare to pseudorandom number generators today, but we haven't done detailed comparisons of that yet. We can see we're seeing picojoules here. In the earlier motivating work, I saw microjoules, but it still requires a lot more to do a more apples to apples comparison. Okay, so that's on generating the random bit streams and analyzing them. And so going forward, I want to show a couple applications we did so far with our models that we've set up. So the first one was one of the things that is common to want to do with these RNGs is to generate samples from a distribution. So you have some arbitrary distribution that you want to represent some kind of particle physics experiment or any kind of data that you have. And then you want to be able to flip your coins and have the probability of getting heads or tails then map on to that distribution. And so we wanted to show that we can do that. So here's just a very simple distribution shown on the right here. So imagine you have a 4-sided die. And so you want to roll a 0 with probability 1/2. So one of them has a 1/2 probability. And then you want to roll 1, 2, or 3 with probability 1/6. That's what's represented here. And we can accomplish that with 2 coins that can be heads or tails. And so 0 will be, actually I wrote this wrong. This should be heads, 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 heads is 0. And then 1, 2, and 3 are tails, 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 heads, or heads, tails. That gives us this probability distribution. And so how do we do this? So we want P to be the probability of heads for coin 1 and Q to be a probability of heads for coin 2. And so we want PQ to be 1/2. And then these other ones all to be 1/6. And that's what's shown over here. So that's what we want to try to get with our MTJ coins. And to do that, we can use this hidden dependence method. So basically, going back once, this equation is over-constrained. And so to solve it, we need to introduce another variable. And so we can do that by using this hidden dependence method. And then we use this library of evolutionary algorithms in Python, or LEAP, and that allows us to output the required weights of our coins to get the certain distribution. And this work was led by Katie and Shuma, and they presented it at ICRC a couple of days ago. So yeah, so they led this part of this project. So basically what we're going to allow is that there's going to be some fraction of the time, R, that these 2 coins have a probabilities P1 and Q1, and then the rest of the time, they're going to have a different probability, P2 and Q2. So you can see what we want to do here is we want to be able to give weights to our coins. So tune it to P1 and Q1 sometimes, and P2 and Q2 sometimes. And we want to do this randomly so that over the times, every time we sample the coins, there's some fraction of the time they're in one weight and some other fraction in another weight. And so if you don't get anything else from this, you can see that how important it is to have a RNG that you can then dynamically tune its weight. So with what we have, we can just apply our bias, either STT bias or field bias, and then at any given time, we can be tuning our weights dynamically. And so we can then use this LEAP to solve and tell us what weights they should have. And then putting it into our RNG simulators, we can see that we can map onto this probability fairly well for the 3 types that we simulated. So you can see the SOTs in blue, the VCMA in green, and the right in orange. So they're not perfect. You know, there's little deviations from a 1/6 here and some little deviations from a 1/2, but we can get pretty close to the desired distribution. And it shows us that the method is there to do this. So here's a second application we showed, and this is for simulated annealing. So maximum satisfiability problems are NP hard, so it's a nice thing to do with our RNGs. And so this particular max stat problem is to find a combination of these X, Y, Z Boolean variables that can satisfy the largest number of clauses. And so in the simulated annealing, we want to have something act as our temperature, and then we want to slowly change that over time until we get to the lowest energy solution. And so here we use the amplitude of the SOT current, or we can also use the amplitude of this VCMA voltage, and we're going to change the amplitude of the current or the voltage, and that's going to act as our temperature. And so here for the SOT case, so this is a little bit different than before, where we were using SOT current to drive the magnetization to the in-plane state, and then we're using STT to bias. Here instead, we're still using STT to bias, but then we can change the amplitude of that SOT current as well. And so this orange curve is for a higher SOT current applied versus our STT current. So this is our S curve. And you can see how the shape of the S curve changes if we have lower SOT current applied, shown in the purple. So we're tuning our S curve basically, and that tuning is acting like our temperature. So then we can put this into a simulator where, again, these magnetic tunnel junctions are the X, Y, Z, and X prime, Y prime, Z prime. These are the MTJs acting as artificial neurons. And then we have their outputs going into a weight matrix, and that adjusts their weight and then back into them. And then we're gradually adjusting this temperature shown in pink. So again, that's the SOT or the VCMA amplitude. And this is also shown here about how it's done. So we have a certain neuron status of 0s and 1s, and then we put it through some weight matrix, and we get some weighted values. And then we change the temperature and do the simulated annealing process. So what we find is that here is our results of, this is the system energy as we apply different iterations of adjusting the temperature. So we do it for 100 iterations, and we get 100% accuracy in identifying the minimum system energy, which happens to be this particular clause and this particular energy. It doesn't really have a unit, it's just a number that's the output, that's the minimum. So we show this for both SOT and for VCMA. And so we can see after very few iterations, we already get down to the lowest solution. And we can do some analysis of the energy required to do that. So for SOT, for our annealing, we went from 5 times 10 to the 11 amps per meter squared down to 1 times 10 to 11 amps per meter squared. So it's a reasonable tuning of current density. And each iteration, the average energy was around 18 picojoules. And for VCMA, we started out with 1.5 volts and then slowly decreased to 1.1 volts to be this annealing process. And there, the average energy was around 305 picojoules, again, because in general, the VCMA was larger energy. So this shows us that combining this easy tunability and the low energy operation is a nice use of these RNGs for these type of simulated annealing problems. Okay, so concluding the first part of my talk, I want to say that magnetic tunnel junctions can satisfy the required characteristics of hardware-based RNGs, and there are many knobs available to control and tune MTJs, which provides versatility for controlling them for whatever our application is. So what we conclude so far is that with uniform materials parameters, the SOT provided the lowest energy. The STT, the stochastic right type, is the most straightforward to implement, since you just have one control knob, you just have STT current and its amplitude. And the VCMA is an interesting approach, but will require changing to higher damping materials. And then we showed that, yes, they can be tuned to match arbitrarily sampled distributions and also applied to simulated annealing. So the last 20 minutes, I'll go to the third part of the talk. And this is the work, like I said, that was done with Chris Bennett and Patrick Shao. So this is changing junctions a little bit, but just a little. So instead of making random number generators, we're leveraging stochasticity, which is related but slightly different, and combining it with these domain wall magnetic tunnel junctions that we've been developing and applying it to Bayesian neural networks. I see someone just made a chat. Have you considered applying this to the maximum subgraph problem? That is a really good question. I think there's a lot of, this was just one example simulated annealing problem, but it can be mapped onto a lot of these other types of simulated annealing problems. And there's other people in our team as well working on other example problems, but I haven't yet. Yeah. Okay. Any more questions? You're welcome to ask. Okay, so yeah, so here we're using 3-terminal magnetic tunnel junctions that have domain wall. So you can see what it looks like here on the left. So basically we have the tunnel junction and we extend out its bottom magnetic layer as shown here. And so this blue and the red are different magnetized regions. And then this white line here is a domain wall. It's the transition between these two magnetized regions that we can push back and forth with current. And we can use that to modify the resistance through this output tunnel junction in the center. And so it's a pretty simple extension of the MTJ, but allows us to have this extra degree of freedom with just domain wall dynamics. And here on the right is the devices that we have been fabricating in our lab. So we can make them act as artificial synapse. To do that, this is a side view of the device. So if we extend out the length of the top tunnel junction, then depending on the relative position of the domain wall along it, we can get out more than just 2 resistance states. And we're not the first ones to work on this. There's a lot of people interested in this device type, but we think we're one of the first ones to show it in a really scaled structure. And so here's the cartoon then of it extended out. And here's the SCM images, and we add in notches to better control over many cycles the domain wall position so we can get it sit in these different notches. So how do these devices behave? On the left here, you can see the resistance of the center tunnel junction as I apply an outer plane magnetic field. And so we can see it has a nice sharp perpendicular anisotropy field loop. And then if we instead apply voltage pulses across the wire, we can start pushing that domain wall and we can monitor the resistance after every pulse. And we can see this is over many cycles that the domain wall will be in one notch, and then it jumps to the next notch, and it really reliably will sit in all 5 of these notches shown here. And so on the y-axis, it's highly stable. On the x-axis is highly stochastic here, because there's any thermal pulse any pulse of voltage has some probability of kicking that domain wall out and moving it to the next notch. So sometimes it comes out really quickly, sometimes it takes a while before it kicks out to the next notch. And so we can think of that probabilistically as shown in the right here, like a state distribution versus right voltage. We can also play around with things like modifying the structure of these devices to tune its behavior. So here we instead made it a trapezoid shape. And here we get out different behavior where now we get less stochasticity on the x-axis here. So for a given voltage, we're more reliably switching it up the track as the domain wall goes from notch to notch. And here there were 3 notches that kept caching the domain wall, even though we put more into the device. Okay, so that's for more on the experiment. You can see that paper I wrote here, this paper. So I'm going to go into our simulation work. So we can further understand just the behavior of these devices as an artificial synapse using simulation. So here are micromagnetic simulations in this paper here, where we analyze their use as artificial synapses. And so here's the domain wall, then looking down on this magnetic wire, and we can have a bunch of notches and move the domain wall back and forth. And so we can, for example, look at its conductance change for ramps up and down. This is for 30 repeated ramps. And whether we drive this domain wall using spin orbit torque, just like we were talking about before, or spin transfer torque. And so we can see we can tune the stochasticity depending on which type we use. But either way, we get pretty nice linear and symmetric behavior of these devices for synapses. And this is in comparison to a couple other synapse candidates shown here. So this is the RAM, less linear and symmetric, but stochastic. ECRAM is nicely linear and symmetric as well. Okay, and then when we have these, we can imagine putting them into the cross points of crossbar arrays for neural networks. Okay, so what about really doing a better job of leveraging the stochasticity and therefore being able to use them for Bayesian neural networks? So Bayesian neural networks have gotten a lot of recent interest because they can encode weights as distributions instead of a deterministic value. And when we think about edge applications of our computers, this is very desired. We want a car to know the confidence of what it's looking at, not just whether it's a cat or a person or a stop sign. And so we can train these using these backpropagation plus this variation inference method. And we can then have uncertainty quantification to provide valuable information about whether our results are noisy or whether they're out of distribution. And so this is depicted here. And so to do this, our team developed this Bayes MTJ, which is going to be used in conjunction with the domain-wall MTJ. So it's now we have the magnetization just in the free layer, randomly processing in time. So it's kind of like that low energy barrier type I talked about at the beginning that's used for p-bits, but instead of having perfect anisotropy, now has magnetization as in-plane anisotropy. So it's randomly fluctuating, and then we can apply a voltage to control how random that fluctuation is, basically. And so again, we simulated this using the LOG macrospin model combined with our domain-wall identical junctions. And one thing that Chris and Patrick nicely came up with is this pulsing scheme to use these together in a circuit. So again, you can see here, so this is the noisy Bayes MTJ combined with these deterministic domain-wall MTJs. And we're going to have two, one for positive weight updates and one for negative weight updates. And these together can then go into, can determine the charge of this capacitor. So that's what we're measuring here in our simulator, the charge of the capacitor over time. So for 0 volts applied to this Bayes MTJ, we can see it's quite noisy. And then if we apply voltage, it gets less noisy. And then we can also simulate the noise of this domain wall sitting at each of these notches. So it also has its own noisiness that can be controlled as well. So there's a lot of knobs we can control here. We can learn a little bit more here about the noise control. This is the noise level over time, and versus applying this voltage, so we can see it go down. And then we can also look here at this noise, and we can do an analytical fit to it compared to a normal distribution. So here's the fitting function that was used. And we can then see how this can represent the Bayesian neural network. So here is looking at the range of the stochastic synapse. And so we can see that these different noisy levels can be nicely represented in this range. Okay, so how does this work then? So we use the Sandia cross-sim simulator to apply this to neural networks. And we evaluated the network on fashion MNIST and also this EMNIST letters, which have a more out of distribution noisy data set. So the fashion MNIST should have less noise and the EMNIST should have more noise. And so to really see how it's doing, we've compared it to two things. One is a software deep neural network shown in green, and then a software Bayesian neural network. And then the orange is the spintronic Bayesian neural network. And so we can see this is the noise density versus uncertainty. So basically the conclusion here is that the spintronic Bayesian neural network very nicely matches the software Bayesian neural network. So it's able to predict the noisiness much better than a deep neural network. Both, so you can see that for the fashion MNIST data set, and then we have also for this EMNIST. And we can better understand the accuracy by looking at this type of curve where we see how under or overconfident our data is. And so you can see the software one, deep neural network, is a lot more overconfident than our spintronic one, which nicely matches the software Bayesian neural network. Another thing we did was gradually transform the fashion MNIST to EMNIST. And so we can see then it's another way to quantify how it's capturing the uncertainty. And so again, our spintronic nicely matches the software Bayesian neural network and does much better than the software deep neural network. And so we then tried to look at how it behaves with higher complexity data sets. So Chris and Patrick applied this to the CFAR 100 data set. And basically there started to be some errors because of the range that we could encode the noise. And so for larger neural networks, it wasn't matching the software Bayesian network as perfectly. But it can still do quite good. So here's another complexity task of street view house numbers. And so our spintronic Bayesian neural network is slightly overconfident because of this limitation in our noise range, but it still is doing a lot better than the software deep neural network. And you can see that here and also here. So we're a little bit higher here than the blue. But if we look at energy, then we can see the benefit of going in the spintronic direction. So here, this was energy consideration of a probabilistic MAC compared to a CMOS implementation. And you can see here for our implementation, as you increase the ray dimensions, our spintronic implementation has a really good energy benefit. We could predict over 100x improvement in large arrays by using spintronic Bayesian neural network. So that's really where the benefits of going to the spintronic solution would come out of. Okay, so to conclude the second part of the talk, I am trying to prove that the smaller on-off ratio we have of the MTJs relative to the other synapses may not be too important as long as we can show these other very important properties of artificial synapses. And we have this spin over torque driven stochasticity and notches that we can use to have tunable stochasticity while also having controllability of where these domain walls are sitting. And then we can also tune the devices via geometry and voltage tuning. And then in this application to Bayesian neural networks, we can see that we can get near ideal inference accuracy for smaller tasks and still very good accuracy for larger tasks with a large predicted energy boost. Okay, so I'm at the end of my talk and with 5 minutes to spare, so I'm happy to take questions.
Thank you, Jeanne.